These are our soil erosion experiments by Megan, Jackie and Ken. Erosion is a process that removes soil particles from where they were formed. Erosion is the movement of soil by water, wind or gravity. Erosion is a natural process which forms the landscape, such as rivers, valleys, mountains, caves and coastal platforms. It is a slow and gradual process that occurs over millions of years. However, human activities such as agriculture and mining have greatly accelerated erosion rates. The global areas of land affected by erosion are estimated at over a billion hectares by water erosion. Also, the impact of erosion on mine sites has the potential to cause stream and river pollution through elevation of sediment loads. Some of the factors affecting water erosion are slope length. If a slope is long, water running down the slope becomes deeper and moves faster, taking more soil with it. Slope steepness. The speed of runoff increases on steep slopes, which increase the power of water. Texture and structure of soil. Soils vary in their ability to withstand the impacts of raindrops. If soils contain a high fine sand and silt content, expansive clay minerals, impervious soil layers, blocky, platy or massive soil structure, they are more susceptible to erosion. Vegetation cover reduces the impact of raindrops on soil and also reduces the speed of water moving over the land. Rainfall intensity. Heavy drops on bare soil cause the surface to seal, which limits infiltration of water and increases the amount of runoff. The two factors that we will concentrate on today are surface roughness. Higher surface roughness of a slope increases the time to runoff, facilitates ponding, enhances infiltration, ultimately reducing erosion. And the rock fragments protect the soil from raindrop impact and overland flow. They reduce the amount of sediment that can be transported, and they reduce the physical degradation of the eroding surface, therefore preserving the original soil structure and infiltration rate. This is known as rock armouring. Erosion rates are reduced proportionately to the exposed surface area and the effective rainfall. Another factor is slope shape. Whether the slope is concave, convex or uniform greatly influences the erosion rate. Concave slopes reduce the amount of erosion because the steepest gradient is at the top of the slope, where the amount of runoff is the lowest, while at the bottom of the slope there is a reducing gradient as the slope length and quantity of runoff increases. And convex slopes typically have higher erosion rates because the steepest part of the gradient is at the bottom of the slope where runoff volume and velocity are the greatest. We ran two experiments. Experiment 1 investigated the effect of different sizes of rock fragments on erosion rates. And Experiment 2, slope shape, the effect of slope shape on erosion rates. So the aims of our experiment was to gain understanding of quantitative measurement of erosion rates and understand how landscape form impacts erosion. And the objective was to conduct irrigation experiments on physical models to quantify factors contributing to enhanced erosion rates in soil. Our hypothesis for Experiment 1 is larger rock fragments will produce less erosion, and secondly that a concave slope will have the lowest level of erosion than either a convex or uniform slope. Okay.
There were two different experiments split into two parts, rock armouring and landscape. The experiment setup, this diagram, broadly captures the equipment and setup used in the experiments. You have a soil tray which is filled with a specific soil. In this case it was a Pilbara soil. There are a set of sprinklers over the tray to simulate rainfall, which is then connected to a computer. This will record the data during the experiment. On the left is where the runoff was collected and hence the erosion of the soil. This was collected in trays and containers which are then weighed. However, the specific setup is different for the inside and outside experiments. For the outside experiments, the focus is on determining the effect of rock armouring on the erosion rate. The setup was slightly different. Larger scale sprinklers were used that simulated multiple large downpour events instead of a continuous event. The rainfall was a lot higher for these experiments. Containers were laid down to be used to calculate rainfall intensity, which averaged as 1.21 times 10 to the minus 7 meters per second. The trays were different to the inside experiment, and these were larger, and just Pilbara soil was used, with erosion captured for 30 seconds every 3 minutes. For the inside experiment, the setup is similar to the first diagram. The focus of this experiment was to measure the effect of changing the shape of the soil on the rate of erosion. A concave, convex and uniform shape were used. The soil used was mostly river sand with a top layer of Pilbara soil, which contains some rocks. The rainfall was constant for the whole experiment at 200 millimeters a second, with erosion captured for 30 seconds every 15 minutes. The data for both experiments was then analysed. For the data analysis, all the data from the different groups was combined. This was then used to produce erosion graphs and to calculate erosion rates. A t-test was also conducted to test for any significant differences between the different treatments.
Okay, so let's move on to the results session. After we collected runoff from the catchment, we put them in the oven and dried them for days. Then we took the dried sediment out, weighed it and used it to calculate the rate of erosion in the catchment. The formula here is the formula we used to calculate the erosion rate for both part 1 and part 2 of our experiment. Part 1 is the erosion rate in soil with and without rock armoring, and part 2 is the erosion rate in soil using different landscape. The experiment was run in 3 times, that is group A, B, and C, as stated in this table. Catchments for group A, B, and C are located side by side and have the same soil type. Therefore, we assume that with the consistent rainfall intensity, soil erosion in all 3 catchments will be the same. Here, we begin the erosion rate analysis by testing the significant difference in erosion rate for soil without rock armoring. 3 sets of paired t-tests is conducted to identify the potential outlier in the replicates. We hypothesize that there is no difference in mean value between the replicates. This means that group A, B, and C are expected to have the same mean erosion rate within 95% confidence interval. It is important to note that the sample size is too small to accept null hypothesis. So we do not reject null hypothesis when t-stats value lies in between the positive and negative range of t-critical two-tail. This table shows that all t-stat values lies in between the positive and negative range of t-critical two-tail. This table shows that null hypothesis cannot be rejected for all scenarios. Therefore, we conclude that erosion rate for group A, B, and C are statistically indifferent, irrespective of the location of catchment. Hence, erosion rate without rock armoring is calculated using the average value of group A, B, and C. So now, let's look at the erosion rate with rock armoring. The experiment setup for this is exactly same as those without rock armoring, with the addition of rock cover. T-test results tell us that mean erosion rate for group A and B is statistically indifferent. However, erosion rate for group C is significantly different from group A and B. This scenario can be explained using this table. Here you can see the t-stat value for group AB lies in between the positive and negative range of t-critical two-tails. Hence, null hypothesis cannot be rejected. However, t-stat for group AC and group BC falls outside the positive and negative range of t-critical two-tails. Hence, null hypothesis for those scenarios are rejected. This means that mean erosion rate for group C is statistically different from group A and B. So, the t-test for erosion rate with rock armor concludes that erosion rate for group A and B are statistically indifferent, irrespective of the catchment location. However, the erosion rate for group C is significantly different from group A and B. Therefore, data for group C is eliminated. The erosion rate without rock armoring is calculated using the average value of group A and B only. This graph shows the rate of erosion in soil with and without rock armor. It shows that soil without armoring experience a higher erosion rate as compared to those with armoring. Note that there is a peak in erosion rate for soil with less rock armor. The peak appeared when runoff is first observed, and this is because without rock armoring, finer materials can be easily removed by precipitation, and the rate of erosion decreases sharply right after all fine materials in the catchment being removed. By large, we notice that rate of soil erosion without rock armoring decreases over time, whereas those with rock armor remains at a relatively constant rate. This is our second experiment, and it is done by using different landscape, which is the convex, concave, and uniform slope. This graph shows that soil in convex slope has significantly higher rate of erosion as compared to those in concave and uniform landform. We did not conduct t-tests for this part of the experiment due to the lack of data we have.
Some of the limitations of our experiment was that soil should be weighed so that the bulk density and hydraulic conductivity can be calculated. Another limitation was that only one experiment was conducted on slope shape. This does not give a reliable result. Also for the slope shape experiment, we assumed that the erosion rate was the same all over the catchment, but this may not be the case. Different rates of erosion occurs at different levels. Therefore, a different method should be used to calculate the erosion rate. For example, toothpicks should be placed along the transect so that erosion at each point can be measured. In conclusion, our first experiment was increased rock armouring reduces the rate of erosion, and for the experiment 2, a concave slope has a reduced rate of erosion compared to convex and uniform slopes.